Unit 5, Lesson 3 is a big one. Solving differential equations. Heck, if you take enough calculus, you're just going to take a few classes on solving differential equations. I always joke with my students, or maybe not always, just for the past couple of years, man. COVID was actually kind of cool. You know, you would hear things about differential equations and that idea on the news. I have no idea if those folks knew what they were talking about, but it was a lot of cool examples. So you don't really, maybe you do have to worry, but you need to be able to identify what a separable differential equation is and a non-separable differential equation is. I'll give you a few examples so you can see the difference. Maybe another way to say that is, you know, if you know what a slope field is, we use slope fields here in AB for non-separable differential equations, like we can't do the calculus on them that we can do with the separable differential equations. So if you have a separable differential equation, you're going to solve it. And you might get a specific solution, you might get a general solution, and the real big difference there is if you have enough information to get rid of your plus C, you can do a specific solution, or you'll have a specific solution. So we're going to integrate each of these. There's just something I want you to know, be prepared for, make sure we're on the right page, however you want to say that. Can I drag this? I can't, darn it. Okay, so the first one, the indefinite integral of x dx, asks if the input variable is x, what has the derivative x? And well, of course, that's x squared over 2 plus a constant. So in the middle, the indefinite integral of y dy, in my mind, asks the exact same question with a different variable. What has the derivative y if the input is y? Well, it's y squared over 2 plus a constant. You know, and by that same logic, we could have done the indefinite integral of r dr. Something like that. It's all the same question. This last one, the indefinite integral of dy, I actually want you to think about something else there. And the question there is, what are you actually taking the antiderivative of if we're integrating dy? Well, we get y plus c, so what we're really taking the integral of is a 1. Like, hey, what has the derivative 1 if the input variable is y? Oh, it's obviously y, maybe plus a constant. So dy dx equals 2. dy dx equals 2 sine x, and dy dx equals x times y are all separable differential equations. You could use the calculus AB techniques to solve these. And what does it mean to separate variables? It means to get the y's, dy's, and no x's on one side, typically the left, and the x's, dx's with no y's on the right. So really all we do there on the first one is multiply both sides by dx. We get dy is on the left, 2dx on the right. We've separated variables. In the middle, dy dx is 2x sine x. Notice on the right-hand side are a whole bunch of x's. So here again, all we have to do, multiply both sides by dx. I, for some reason, have an eraser. Is that a pen yet? Pen? Multiply both sides by dx. And you can think of dx divided by dx as 1, or the change in x divided by change in x is always the same, whatever you want to say. On the right-hand side, dy over dx is x times y. We have two things. So you have the y on the right, we need to move over with the dy, and we have the dx on the left, we need to move over to get with the x. So we rewrite that as 1 over y dy is equal to x times dx. Okay. So if we can separate variables, we can solve. We'll talk about what that means in a second. But the next step would be to put integrals on both sides of each of these equations, and then obviously integrate. Before we do that, let's look at what non-separable differential equations look like. So 2x minus y, you might think, well, I don't know, it doesn't seem like it's all that different from the ones we just looked at. So let's try to get the x's, dx's, and no y's on the right, and the y's and dy's, no x's on the left. So, you know, maybe you just think, okay, I'll multiply both sides by dx, and dy is equal to 2x dx minus y dx. Well, that seems pretty good. This y. We need to get rid of the y. And you have two choices. We can divide by y, which won't work, or we can add y times dx, which won't work. So notice if we add, let's see, we'll get dy plus y dx, and then 2x dx stays where it is. Notice that doesn't work. I suppose we could divide by y. We divide by y. We could, but that's going to give us dy over y is equal to plus dx is equal to 2x over y times dx. Well, that didn't help. Well, I mean, it's in the name. These are non-separable. Well, maybe we go back. Maybe we do something else instead. Okay, so what if we added? Maybe we add, and so we'd get dy plus y dx is equal to 2x dx. And then, all we need to do is get rid of the dx, so we'll divide both sides by dx. And dy over dx, oh darn it, plus y is equal to 2x. Dang, that's almost what we started with. And then on the right-hand side, I know some of you actually know sign of a product, but whatever. You know what you can see is if you multiply both sides by dx, we really can't touch that y inside a sign. Probably the only way we know how to get to that y inside of sign is to do inverse sine of both sides. And inverse sine of dy dx is going to be equal to xy, and now the dx is all locked up. Usually you'll have things more like on the left where you have an addition or subtraction, at least in AP Calculus AB. Okay, so what would it mean to solve? We're going to find a general solution first. A specific solution is trivial once you know how to find a general solution. And basically what we're looking for is y is equal to a whole bunch of x function stuff, meaning the y is on the left and just a whole bunch of x's on the right. And that function has as its rate of change 2x sine x, the differential equation we started with. So what do? Well, we separate variables. We multiply both sides by dx, and we get dy is 2x sine x dx. And then just because of the way College Board grades, expects things, we're actually going to write separation of variables twice. Once without integrals, then once with integrals. And I'll show you why in just a second. They consider it a pretty big deal. So on the left-hand side, the antiderivative of 1 with respect to y is y. But on the right-hand side, you should look at 2x sine x and think, man, I can't do that yet. Unless you know integration by parts. And if you know integration by parts, I can't imagine, that you need this video. Okay, this one, dy dx equals x times y, is something we can find a solution of, and when we're done, we're going to have y equals some function of x, and that's going to have xy as its derivative. It's kind of weird, but I think we can do it here. So first thing, and you've already seen this differential equation, we are going to divide both sides by y, or multiply both sides by 1 over y, and multiply both sides by dx. So we've separated variables. Y's and dy's on the left, no x's. X's and dx's on the right, no y's. So we put integrals in front, and again, it's something I've had a lot of success with my kids, and I'll show you why in a few minutes. So probably start on the right. What has the antiderivative of x? What has the derivative x? X squared over 2 plus a constant. And on the left-hand side, antiderivative of 1 over y is natural log of the absolute value of y. Okay. So in general, we're actually not done, but in general, the reason this is a general solution is that plus a constant. And if we have an ordered pair, which is called an initial condition, if you have more information, we'd be able to fill in that plus c. Now, remember, we're supposed to get y is equal to some function, so we need to get rid of that natural log and that absolute value. So the inverse of natural log is e to a power. We'll raise both sides as exponents of e. And then we get absolute value of y is equal to e to the c, e to the x squared over 2. And you might be thinking, wait, what the heck happened? Well, notice that's e to a sum of exponents. You know, just think, what would you do if you had e to the x squared times x? I'm sorry, I said e. What would you do if you had x squared times x cubed? That'd be x to the power 2 plus 3. We're just doing that in reverse. And the reason we're doing that in reverse, it'll come up when we get to some applications. This e to the c, that actually has some meaning on its own, and it's the initial amount. You're going to see that with exponential growth and decay, half-life, things like that. Anyways, so we also are going to get rid of the absolute value right there. There's a plus minus on that y inside. And so when we get rid of the absolute value, we bring that plus minus to the other side. Ooh, let's get rid of that guy, that guy. All right. So dy dx is equal to the square root of x. Can we get a general solution here? What does that mean? We're going to y equals some function and only x's. Notice that's what we got down here on the last one. Y on the left and only x's on the right. Okay, can we separate variables? Sure. dy, and it's probably easiest to put that square root of x as an exponent, so x to the 1/2 dx, and then again we'll write integrals on dy and an integral on 1/2, or x to the 1/2 dx. Antiderivative of 1 dy is y, and then we're going to do x to the 3/2 multiplied by a 2/3, don't forget that plus c. Oh, that was actually a whole lot easier. And the reason that was a lot easier than the previous one is there's just that one x sort of thing on the right. So that's probably not going to show up on free response. Now, you also need to be able to change things back. If you can't change things back into radicals, well, we're going to get you on multiple choice. So we expect you to, if you have a radical to begin with, square root of x, we expect you to change things back at the end here, 2 root x all cubed, all divided by 3 plus c. There are lots of ways to write that. Okay, here you go. So you're going to see separation of variables has a special place in AP scoring. I think you should show the separation every time, twice. That's going to train your brain that, hey, this is really important. So this is from 2018, I think. It's been a few days since I made this PowerPoint, but whatever. The left-hand side, whatever, it's separating variables, there's the work. We're going to practice that a lot. I actually want you to look at the right-hand side, because the right-hand side is the interesting one. And for most things, College Board, you know, if you make an error, like you got an antiderivative wrong or something, well, you know, they keep grading because, you know, there's still a lot of good calculus that you can show what you know. Well, notice down here, if there's no separation of variables, well, they're not going to grade anything. You can't get a point for an antiderivative. You can't get a point for constant of integration and using the initial condition. You can't get any points whatsoever. They just stop grading. And so because of that, in my class, and if you're watching this, whatever, show the separation every time twice. Because you're going to be like, separate variables, it's important. Separate variables, it's important. Okay, we only need to do one example to do a particular solution, because the only difference is, well, we, in this case, notice, have an ordered pair, 1, 0, which will allow us to fill in the x and y and get that constant. Okay. So dy dx is equal to e to the x minus 6x squared. That's clearly separable. It only has x's on the right. So we're going to find the solution curve that passes through 1, 0. So obviously we separate variables. Dy is e to the x minus 6x squared, give it a hug, times dx. And then we want to make sure our solution is graded. We put integrals on that. The integral of dy is the integral of e to the x minus 6x squared dx. Pretty straightforward antiderivatives. Antiderivative of 1 with respect to y is y. Antiderivative of e to the x with respect to x is e to the x. Antiderivative of negative 6x squared is negative 2x cubed. Don't forget your plus c. You don't need to write that this is a general solution, but just as a reminder, you're probably going to find it on the way. I guess the exception is exponential growth. You don't necessarily have to find everything on the way. Anyways, so how are we going to get that plus c filled in? And to most of you, the answer is obvious. You know, there's this 1, 0. We're going to use 1, 0. And so we put 0 in for y, 1 in for x. So e to the first minus 2 times 1 cubed plus c. Add 2, subtract e, and that c is equal to 2 minus e. I suppose there's another pitfall here. A lot of people think, sweet, I found c, I'm all done. Well, you're done finding c, but your job was to find the particular solution. The particular solution is y equals e to the x minus 2x cubed plus that 2 minus e. That function, well, here's why it's the solution. E to the x minus 2x cubed plus 2 minus e has the derivative e to the x minus 6x squared, what we started with. And also it contains the point 1, 0. Okay, now you just have to practice.